So here are the generalizations about atomic radii trends. As you go down a group, the atomic radii increases. With increasing principal quantum numbers, more atomic shells or orbitals, groups of orbitals, are being added. And these are further and further away from the atom's nucleus. As you go from right to left across a period, atomic radii increases. Going right to left, the effective nuclear charge decreases. So the ability of the nucleus to pull on the outermost electrons must decrease. The size of the atoms increase when going from the noble gases toward the alkali metals. So let's look at our first example. Using only a periodic table and your knowledge of the periodic trend for atomic radii, arrange the following atoms in order of increasing atomic radii. So let's look at the answers to these three examples. When you look at silicon, aluminum, and magnesium, what you notice is that magnesium is furthest to the left on the periodic table, aluminum is right across from it, and silicon is right next to it as you go towards the right-hand side of the periodic table. Since magnesium is the farthest left, it must be the largest. And since silicon is the farthest right, it should be the smallest. Aluminum should be in the middle of the three. When looking at phosphorus, arsenic, and antimony, this is going down a group. Phosphorus is near the top of the group, right under nitrogen. Arsenic is right below it, and antimony is below it. Remember that you're adding orbitals as you go down the periodic table, and there's more core electrons to shield the nucleus from the outer electrons. Therefore, phosphorus should be the smallest, and antimony should be the largest, with arsenic being in the middle. The same trend is also seen for silicon, germanium, and tin. Silicon is at the top of the group, germanium is next, and then tin is at the bottom. So the order of the elements from smallest to largest should be silicon, germanium, tin. Next, let's talk about ionic radius. Ionic radius is the radius of a cation, which is a positively charged ion, or an anion, a negatively charged ion. Now, when we think of the formation of cations and anions, we can think of it as an electron transfer, as I'm showing at the bottom. When lithium atom and fluorine atom come together, one electron is transferred from the lithium to the fluorine to produce lithium 1 plus and fluorine minus. Now, what you'll notice by just this example, by looking at this example, is that lithium atom is large, but lithium 1 plus cation is small. Fluorine atom is small, but fluorine 1 minus is larger. This is always true. Cations are always smaller than the atoms from which they are formed, and anions are always larger than the atoms from which they are formed. Now the question that arises at this point is why? Why are cations smaller than their atoms and anions always larger than the atoms they originate from? Cations are always smaller because you remove an electron. The effective nuclear charge increases a little bit because you have one less electron to pull on with the nucleus. So you see an atom go from bigger to smaller since the nucleus is pulling better on the outer electrons. Anions, on the other hand, are always larger because you've added more electrons. The nucleus doesn't as effectively pull on those extra electrons, so what you see is an atom get larger. Now, by looking at the periodic table, you can't easily tell a trend in the sizes of radii, or of ionic radii. I just want to point out the following. As you go down a group, the general trend in ionic radii is the same as atomic radii. It increases in size as you go down a group, regardless of whether it's cations, as shown with the alkali metals or alkaline earth metals, or anions, as shown here with the halogens or the chalcogens. Now, when you go across a period, it depends on if you form cations or anions, of course, on how the trend in size is going to go. But if you compare the alkaline earth metals to the alkali metals are always bigger than the alkaline earths because of two factors. First, the alkali metals can only form +1 cations, whereas the alkaline earths can form 2. Furthermore, the alkaline earth metals have one more proton than their neighboring alkali metals. So we expect the alkaline earth metals to be alkaline earth metal cations to be smaller than the alkali metal cations. So this slide just reinforces what I said on the last slide. As you go down a group, the ionic radius increases, much like when you look at atomic radius. The first example graph is for the alkali metals, and the second example is for the halogens. The blue line on the first graph is the sizes of the alkali metal atoms. Notice that the red line is for the alkali metal cations. They're always smaller. However, you see the same general trend if you compare cations to cations or atoms to atoms. As you go down the group, the ionic radius increases, much like when you go down a group, the atomic radius increases. When looking at the halogens, this red line at the bottom is for the halogen atoms. When you look at their -1 anions, the sizes of their anions are always bigger than the atoms. However, as you go down the group, the size increases. So now, I want you to take a moment and arrange the following ions in order of increasing radii: Ca2+, S2-, K+, and Cl-.